going to talk neurotransmitters in these notes, and I am hoping that we find 5 minutes in class to watch this video, but 7th grade, I don't know, because of not having Monday. Even people, I think we can. And so it's really interesting to me how these companies, they're so smart, and they are changing our brains, and we don't even know it. So it's a really interesting video, and I want to talk more about it hopefully in class. If we don't get there, I put the YouTube little, that is an address, I guess, up so you can watch the video. It's 5 minutes of your time, but it's really interesting. And I think everybody, has a phone, and if not, you will someday, and just see how it's changing your brain. So it's neurotransmitters, not brains. But what we are trying to do is be able to recall the 3 types of synapses, and then discuss how structure leads to function in a synaptic connection. Now that probably won't be as strong with these notes. We will strengthen that second walk away next week with some activities. So a synapse is when 2 neurons meet. They can't make direct contact. Instead, there's a little itty bitty gap in between there, and it's called a synaptic cleft. So it's just a little bit of vocab to begin with. So synapse is a spot where 2 neurons meet. And then the synaptic cleft is the little gap in between them. So I just drew it, labeled it, and said, there are my notes. Okay? Just trying to use less words. Now, types of synapses. I love whoever made these. They were the best because it tells you who's talking in the name. You can't ask for better. So axodendritic is an axon talking to a dendrite. Most of our synapses should be axodendritic. But if it's an axon talking to a soma, talking to a cell body, then it's axosomatic. And if it's an axon talking to an axon, they can do that, not very often. But if it's an axon talking to an axon, then it's axoaxonomic. Yay, namer of synapses, they make sense. And so I kind of drew that exact diagram, but I can't draw, so this is as good as I could get, and I tried to color code it, and then I put my vocab words at the top. I'm sure you'll do better than I did. That was me trying. And so because there's this little gap, and electricity cannot make jumps, so the action potential can't jump from one neuron to the next, we have to use neurotransmitters. So neurotransmitters are chemicals that are released into the synapse and absorbed into the next cell, and they transmit information. They say one of 2 things. They might say, have another action potential! So they might excite the next neuron. Okay, and they are going to pump it up, get it to have another action potential, open up those sodium channels, let's go. Or they will inhibit, right? They say, stop, whoa, stop the message. You might think, what? Why would we want a message stopped? Sometimes we do. Okay, so sometimes we do. And as we get into some different examples next week, we may try to dig in a little deeper. I can tell you one thing I want inhibited, and that's pain, right? I don't want to feel pain, but I do want to feel pain. So I don't like feeling pain because it hurts, but I do want to feel pain because that's the difference sometimes between life or death. There are some people who feel no pain. They're very, very rare, and I could not imagine being their mom because feeling pain saves your life, right? As a kid, you try things, and it hurts, so you don't do it again. But you won't believe your parents. For example, we had a space heater because our son's room gets really cold. And I would be like, buddy, this is hot. Don't touch hot, right? And he's just little, he's like 2. And he was like, okay, mom. And then I'd be like, it's hot. Don't touch it. And he was like, shh, puts his hand right on the space heater, right? He took it off very quickly. So he just had a little 1st-degree burn. It wasn't bad. But if you didn't feel pain, why would you move your hand? You would never believe your mom. You would just be like, yeah, mom, no pain. Could you imagine having a child like that? It would scare me. Oh my gosh, it would scare me. How do you get your kid to survive if they don't feel pain? So as much as I want pain to be inhibited, it's also there. It's a very, very clear message. Stop doing something, right? Something's not right. You need to fix it. But prolonged pain, I'd like to inhibit. So again, I just tried to put a little sign by each so I remember the difference between the 2 and just summarized it. All right, so to understand this, we have to realize we have a presynaptic neuron that releases the neurotransmitter and a postsynaptic neuron after the synapse that has the receptors. So the message goes from the presynaptic neuron to the postsynaptic neuron. I'm trying to keep this pretty simple for you. So just a little picture of a presynaptic neuron releases the neurotransmitters, postsynaptic neuron has the receptors. So what are the 4 stages? And again, this could get deeper. We're going to just summarize in 4 stages. The first one is we have to make the neurotransmitters. So synthesis means to make. We have to store those because if we have to make them when we need them, that's slow communication. So we're going to make the neurotransmitters. We're going to store them. That way we can use them faster. When we need them, they're there. So the cell body makes the neurotransmitters. They're stored the axon terminal because that's where they'll be released. And they are released in step 2. And so there's this additional stuff we didn't talk about with action potentials, but at the end of the axon, calcium rushes in during the action potential. And that additional, that influx, that calcium coming in tells the neurotransmitters to be released. So if you want this in more detail, because you're like, I'm going to further my anatomy career, then these steps tell you more details about that step 2. But we're just going to say step 2 is the neurotransmitter gets released. So we make it and we store it for step 1. We release it for step 2. It goes to the receptor for step 3. So it binds to the postsynaptic receptor, and shape matters. So these are examples from next week, and we will look at how a lot of illegal drugs, and marijuana being legal in some states, fit into a receptor. They mimic the shape. They have the same shape as a normal neurotransmitter receptor, and that tells the body the same communication as your normal neurotransmitters. We're going to look at all this stuff next week. It's a little preview. So then step 4, we have to make the neurotransmitter become inactive. So maybe we destroy it, degradation needs to break down, or maybe we recycle it, we pick it back up. But either way, we need the message to stop. Right? We need the message to occur for just the amount of time we need it to, but then we need it to stop. Okay, message needs to be sent and done. And some drugs prevent that reuptake, so the message continues and continues and continues, which maybe you're like, hey, that's not so bad if it's a feel-good message, but then it becomes harder to feel good the next time, and the next time, and the next time, and that's why people increase the amount they do, and the side effects of a lot of drugs is death, and again, never good. So what I did was just kind of summarize those 4 steps. I used a lot of words this time. I did really make sure to include, though, a shape being important to the receptor and the neurotransmitter. I would like you to add a few more pictures. So this is the part, although I've written the words, add some more pictures, right? So you're going to turn in this part in particular, and I want to see some more pictures. So think through, what could you do? And then this you don't have to write down, but these are some neurotransmitters that we will talk about. Dopamine, which can both stop messages and excite messages, so it can stop and go, and do both. And that's a real good feel-good one to burn. Okay, serotonin is also another one that's pretty big in the brain, and it inhibits dopamine, so it's going to stop dopamine. And acetylcholine then is a big one for your muscles, and it's going to tell your muscles, hey, guess what? Have an action potential. So every time the motor neuron gives its message to the muscle, it releases acetylcholine. So the action potential, because muscle cells, they cannot have electricity going through them, unless we're talking the heart, and more to come on that in February. But a normal skeletal muscle, no electricity. So the action potential goes down the axon, and then acetylcholine gets released, and the muscles say, move, and there you have it. So this one is pretty good, and we'll see if we have time, and if we have time, we'll watch it. If not, I'll figure things out. So I know that was fast, but there are your neurotransmitter notes.